Max Planck, one of the most influential physicists in history, was born on the 23rd of April 1858 in the city of Kiel, Germany. His early life was marked by a profound curiosity about the world around him, a curiosity that would later fuel his groundbreaking contributions to the field of physics. Planck came from an academic family. His father was a law professor at the University of Kiel, and his grandfather was a distinguished philosopher. Growing up in such an intellectual environment undoubtedly shaped his academic and scientific pursuits. Planck's academic journey began at the University of Munich, where he initially studied physics. His passion for the subject was evident from the outset, and he quickly made his mark as a student. After completing his undergraduate studies, he continued his academic journey at the University of Berlin, where he studied under the guidance of the renowned physicist Hermann von Helmholtz. It was at Berlin that Planck would begin to delve deeply into the emerging field of thermodynamics, a discipline that would play a crucial role in his later work. The scientific landscape during Planck's early years was dominated by the established theories of classical physics. The laws of thermodynamics, formulated by scientists like Rudolf Clausius and William Thomson, Lord Kelvin, were seen as fundamental principles that governed the behavior of energy and matter. Similarly, the laws of electromagnetism, discovered by James Clerk Maxwell, provided a comprehensive understanding of the relationship between electricity, magnetism, and light. The prevailing belief in the scientific community was that these classical laws could explain virtually all physical phenomena. However, this belief was about to be challenged, and Max Planck would be at the forefront of this revolution. During the late 19th century, one of the most perplexing problems in physics was the issue of blackbody radiation. A blackbody, in physics, is an object that absorbs all electromagnetic radiation that falls on it, and it also emits radiation depending on its temperature. The problem arose when scientists tried to calculate the spectrum of radiation emitted by a black body. Classical physics, which worked perfectly well in most situations, was unable to accurately describe the way in which a black body emitted radiation at high frequencies. The predicted radiation intensities skyrocketed at short wavelengths in a phenomenon known as the ultraviolet catastrophe. This prediction was in stark contrast to experimental observations, which showed that the radiation intensity did not increase uncontrollably, but instead followed a well-defined pattern known as Planck's law. Physicists were at a loss, as no classical theory could explain this discrepancy. Many attempted to solve the issue by adjusting existing theories, but none were successful in fully accounting for the observed experimental results. This challenge in understanding blackbody radiation was a fundamental issue that threatened to undermine the very foundations of classical physics. The stage was set for a revolution, and Max Planck would be the scientist to lead the way. In 1900, while investigating the problem of blackbody radiation, Planck made an unprecedented leap in thinking. Planck had already been investigating the mathematical nature of radiation and had been grappling with the inadequacies of classical physics in explaining the behavior of light and heat at atomic and subatomic levels. He realized that the classical theory of radiation, based on the continuous nature of energy, could not explain the observed phenomena. The key to solving this problem, he believed, lay in the idea that energy is not emitted or absorbed in a continuous manner, as classical physics suggested, but rather in discrete packets, or quanta. This was a radical departure from the established views of the time. Energy, according to Planck's hypothesis, was quantized, meaning that it existed only in certain discrete amounts. Each of these discrete amounts, or quanta, was proportional to the frequency of the radiation. Planck introduced a mathematical constant, later named Planck's constant, which represented the smallest possible unit of energy. The formula he proposed, E equals h/NIU, where E is energy, h is Planck's constant, and NIU nu is the frequency of the radiation, became the cornerstone of his theory. This equation suggested that energy could only be emitted or absorbed in discrete quantities, with the size of each quantum being determined by the frequency of the radiation. This insight was a key moment in the birth of quantum theory. Planck's work was not an isolated endeavor. It was a response to the pressing issues that had emerged in physics, particularly in relation to the nature of light and heat. Before Planck, the dominant theories in physics, such as Newtonian mechanics and the laws of thermodynamics, viewed energy as continuous. The notion that energy could be quantized was a concept that was almost inconceivable at the time. However, Planck's insight provided a simple yet powerful solution to the blackbody radiation problem. His theory explained why the radiation intensity of a black body followed a specific distribution and why the ultraviolet catastrophe did not occur. Although Planck's quantum theory was groundbreaking, it was not immediately accepted by the scientific community. Many of his contemporaries were skeptical of the idea of quantized energy, as it contradicted the long-held belief that energy was continuous. However, Planck's theory was based on sound mathematical principles, and over time, it gained traction among physicists. It provided the first real explanation of blackbody radiation, and it soon became clear that Planck's hypothesis had profound implications for our understanding of the physical world. One of the most remarkable aspects of Planck's work was that it laid the groundwork for the development of an entirely new field of physics, quantum mechanics. Planck's discovery of energy quanta would go on to influence some of the greatest scientific minds of the 20th century, including Albert Einstein, Niels Bohr, and Werner Heisenberg. In fact, Einstein's work on the photoelectric effect was heavily influenced by Planck's ideas. Einstein extended Planck's concept of quantized energy to explain the phenomenon of light emission from metal surfaces when illuminated by light of a certain frequency. This work ultimately earned Einstein the Nobel Prize in Physics in 1921. In addition to his contributions to quantum mechanics, Planck's work also had a profound impact on the development of thermodynamics and statistical mechanics. His insights into the quantization of energy helped to refine the understanding of the behavior of matter at the atomic and molecular levels. His work on radiation also played a crucial role in the development of statistical mechanics, a field that seeks to explain the behavior of large systems of particles in terms of the statistical properties of individual particles. Max Planck's scientific journey was not without its challenges. He faced considerable opposition to his ideas, both from his contemporaries in the scientific community and from the prevailing paradigms of classical physics. Despite these challenges, Planck remained steadfast in his beliefs, and his determination to find a solution to the problems of blackbody radiation led to one of the most significant breakthroughs in the history of science. Throughout his career, Planck received numerous accolades for his contributions to physics, including the Nobel Prize in Physics in 1918. However, he never fully realized the magnitude of his impact on the world of science. In his later years, Planck reflected on his work and expressed amazement at how his ideas had shaped the course of modern physics. He once said, "Science cannot solve the ultimate mystery of nature, and that is because, in the last analysis, we ourselves are part of the mystery that we are trying to solve." Max Planck's legacy extends far beyond his own time. His discovery of energy quanta and his formulation of the quantum theory laid the foundation for the revolution in physics that would follow. The advent of quantum mechanics would go on to transform our understanding of the universe, from the behavior of subatomic particles to the nature of space and time itself. Today, Planck's constant remains a fundamental constant in physics, and his work continues to inspire physicists around the world. Planck's contributions to science were not limited to his theoretical work. He was also a passionate advocate for the importance of scientific inquiry and the pursuit of knowledge. Throughout his life, he emphasized the importance of curiosity, creativity, and perseverance in the quest for scientific understanding. He once remarked, "The true scientist does not seek fame, but only the joy of discovery." This spirit of inquiry and discovery is what has kept Max Planck's legacy alive for over a century and continues to inspire generations of scientists. Max Planck's journey from a curious student in Germany to one of the most influential physicists in history is a testament to the power of intellectual curiosity and perseverance. His work changed everything. It challenged the established understanding of physics, it paved the way for the development of quantum mechanics, and it helped unlock the mysteries of the universe. Max Planck's story is one of groundbreaking discovery, unyielding determination, and a lasting legacy that has shaped the world of science for generations to come. As Max Planck's work on black-body radiation and the concept of quantized energy gained traction, his ideas became the foundation for an entirely new branch of physics, quantum mechanics. However, it was not immediately evident how revolutionary his discovery would become. The scientific world was still heavily entrenched in the classical physics that had served as the cornerstone of the field for centuries. Planck's introduction of quanta was a radical departure from the continuous view of energy, and many scientists found it difficult to accept. Yet, Planck's courage to challenge the existing paradigm and his perseverance in the face of skepticism eventually led to one of the most profound shifts in our understanding of nature. The year 1900 marked the beginning of a new era in physics. Planck's equation, E equals h nu, where E is energy, is Planck's constant, and nu is the frequency of the radiation, laid the groundwork for the development of quantum theory. Planck had arrived at this equation through a combination of empirical data and theoretical ingenuity. It was an equation that applied to the energy of oscillators within a black body, explaining how radiation emitted by a heated object was quantized rather than continuous, as had been assumed before. By doing so, Planck resolved the long-standing problem of black-body radiation that had confounded scientists for years. Despite the immediate success of Planck's formula in explaining black-body radiation, he himself did not fully grasp the implications of his work. Planck believed that his quantization hypothesis was a temporary measure, a mathematical trick to resolve the immediate problem of radiation, rather than a fundamental shift in our understanding of the universe. In his early years, Planck continued to adhere to the classical idea that energy was fundamentally continuous, and it was only later that he fully realized the depth of his contribution to the emerging field of quantum mechanics. For Planck, the quantum revolution was not something he anticipated. However, as time went on, other scientists began to build upon his work and explore the broader implications of quantization. The first major breakthrough came from Albert Einstein, who, in 1905, extended Planck's ideas to the phenomenon of the photoelectric effect. Einstein proposed that light itself was quantized, made up of particles called photons, which could transfer energy to electrons in a metal, explaining the photoelectric effect that had been puzzling scientists for years. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, further cementing the importance of Planck's discovery. The next critical development came from Niels Bohr, who applied quantum concepts to the atom. Bohr's model of the hydrogen atom, developed in 1913, incorporated Planck's idea of quantized energy levels. Bohr proposed that electrons in an atom existed in discrete energy states and could only transition between these states by absorbing or emitting specific amounts of energy in the form of quanta. This model successfully explained the spectral lines of hydrogen, which had previously been difficult to understand using classical physics. As the years passed, more and more physicists began to embrace Planck's ideas, and quantum mechanics began to take shape. Max Born, Werner Heisenberg, and Erwin Schrödinger, among others, played pivotal roles in developing the formalism of quantum mechanics. The theory that emerged from their work was radically different from anything that had come before. Quantum mechanics introduced the idea of wave-particle duality, the uncertainty principle, and the notion that the behavior of particles could only be described probabilistically. These ideas were fundamentally at odds with the deterministic view of the universe that had been championed by classical physics. The impact of Planck's discovery on the field of quantum mechanics cannot be overstated. His introduction of the quantum hypothesis provided the first step toward a complete overhaul of our understanding of the physical world. Where classical physics had struggled to explain the behavior of matter at the atomic and subatomic levels, quantum mechanics provided a framework that could describe the strange and counterintuitive behavior of particles in the quantum realm. Planck's work also laid the foundation for the development of quantum field theory, which has since become the central framework for understanding fundamental forces and particles in the universe. In addition to his contributions to quantum theory, Max Planck's work had a profound impact on other areas of physics, particularly thermodynamics and statistical mechanics. The concept of quantized energy levels helped refine our understanding of heat and temperature at the atomic level. Planck's work on the statistical nature of thermodynamic systems provided a deeper understanding of entropy, a concept central to the second law of thermodynamics. These insights have influenced a wide range of scientific disciplines, from chemistry to cosmology. As quantum mechanics developed over the 20th century, it became clear that Planck's work was not just a breakthrough in theoretical physics, but also a catalyst for technological innovation. The principles of quantum mechanics have led to the development of technologies that are now integral to modern life. The invention of the transistor, the laser, and magnetic resonance imaging, MRI, are just a few examples of the practical applications of quantum theory. These technologies have transformed the fields of electronics, telecommunications, medicine, and computing, profoundly altering the way we live and work. Today, Max Planck is remembered as one of the fathers of quantum mechanics, and his legacy continues to shape the direction of scientific research. His work has led to a deeper understanding of the fundamental nature of reality, and it has paved the way for innovations that were once the realm of science fiction. Planck's contributions are especially significant because they represent a paradigm shift in our understanding of the universe. Before his work, the physical world was seen as a continuous, predictable system governed by classical laws. After his work, the universe was revealed to be a place of uncertainty, where particles behave in ways that are fundamentally unpredictable, governed by the strange and fascinating principles of quantum mechanics. Max Planck's impact extends beyond the realm of physics. His ideas have influenced other disciplines, including philosophy and even the arts. The notion of a discrete, quantized universe has inspired new ways of thinking about reality, time, and space. In the realm of philosophy, Planck's work has challenged our understanding of causality, free will, and the nature of human consciousness. In the arts, quantum mechanics has inspired a new wave of artistic expression as artists explore themes of uncertainty, indeterminacy, and the unseen forces that shape our world. Max Planck's discovery truly changed everything. His quantum hypothesis was not just a solution to a particular problem in physics, it was the beginning of a new era in science, one that would revolutionize our understanding of the universe. It set the stage for the development of quantum mechanics, a theory that has transformed the way we think about the nature of matter, energy, and the very fabric of reality. Planck's work continues to inspire physicists, engineers, and thinkers across the globe, and his legacy will remain a cornerstone of scientific inquiry for generations to come. The state of classical physics, at the time of Max Planck's discovery, was one of relative confidence and success. Scientists had made significant strides in understanding the physical world through well-established laws, such as Newton's laws of motion, the laws of thermodynamics, and Maxwell's equations describing electromagnetism. These principles had provided explanations for a vast array of phenomena, from the behavior of everyday objects to the propagation of light and the laws of heat. However, by the late 19th century, several important challenges emerged that classical physics could not adequately address, which created a sense of intellectual uncertainty in the scientific community. One of the most pressing problems that confronted physicists during this period was the issue of black body radiation. A black body, in the context of physics, refers to an idealized object that absorbs all electromagnetic radiation falling on it and re-emits radiation based on its temperature. The study of black body radiation was central to understanding how heat and light interacted with matter. It was believed that a perfect understanding of black body radiation would provide insight into the very nature of heat and the emission of light. However, existing theories could not explain the spectrum of radiation emitted by a black body, especially at high frequencies, which was a growing concern for the scientific community. The problem of black body radiation became known as the ultraviolet catastrophe because classical physics predicted that as the temperature of the black body increased, the amount of radiation emitted at shorter wavelengths in the ultraviolet region of the spectrum would increase without bound. This was in stark contrast to experimental observations, which showed that the radiation emitted at shorter wavelengths eventually decreased after reaching a peak and did not continue to grow infinitely. The inability of classical physics to explain this discrepancy posed a significant challenge to the prevailing understanding of physics. Classical physics, particularly the Rayleigh-Jeans law, attempted to describe the distribution of energy emitted by a black body. According to this law, the intensity of radiation should increase with the square of the frequency at higher frequencies, leading to an unbounded increase in energy. This theoretical prediction suggested that objects heated to high temperatures would emit infinite energy, which, of course, was physically impossible and contradicted experimental data. Despite efforts by scientists like Lord Rayleigh and James Jeans to refine the law, it became clear that the classical theories could not provide a satisfactory explanation. This dilemma led to a crisis in the scientific community. Classical physics, while successful in many other areas, had reached an impasse when it came to explaining certain phenomena, especially those occurring at microscopic or atomic scales. Physicists recognized that their current framework was incomplete, and there was growing realization that new ideas were needed to resolve these contradictions. The problems with blackbody radiation became emblematic of the limitations of classical physics, and the search for a new theoretical framework began. It was in this context of uncertainty and intellectual ferment that Max Planck entered the scene. As a respected physicist, Planck had been following the developments in thermodynamics and statistical mechanics, and he was particularly focused on the problem of radiation. At the time, the prevailing theory of heat and light was based on the idea of continuous energy, with the assumption that energy could be distributed evenly across the spectrum of radiation. This was consistent with classical thermodynamics, which treated energy as a continuous quantity. However, the failure of these theories to explain black-body radiation prompted Planck to reconsider these assumptions and take a new approach. Planck's breakthrough came in 1900 when he developed a formula to describe the spectrum of radiation emitted by a black body. He proposed that the energy emitted by the oscillators inside the black body could only exist in discrete amounts, or quanta, rather than being continuous. This was a radical departure from classical thinking, which had treated energy as a continuous and infinitely divisible quantity. Planck introduced a constant, now known as Planck's constant, which was fundamental to the relationship between energy and frequency. His formula, expressed as E equals h nu, where E is energy, h is Planck's constant, and nu is the frequency of the radiation, provided a way to describe the energy of these discrete packets of radiation. Planck's hypothesis that energy was quantized was initially met with resistance. It was difficult for many to accept the idea that energy was not continuous, as this contradicted the long-held views of classical physics. Furthermore, Planck himself did not fully appreciate the profound implications of his own discovery. At first, he thought of the quantization of energy as a mathematical convenience rather than a fundamental aspect of nature. He believed that his formula was merely a tool to solve a specific problem and did not anticipate the radical changes it would bring to the field of physics. Nevertheless, the success of his formula in explaining the black-body radiation problem convinced other physicists to take notice. Planck's work on quantized energy laid the foundation for what would later become known as quantum theory. It was the beginning of a new era in physics, one that would challenge the classical view of the universe. Planck's theory, however, was just the first step. It was Albert Einstein's later work on the photoelectric effect, building upon Planck's idea of quantized energy, that would fully establish the concept of photons and the wave-particle duality of light. Einstein's insight into the particle-like behavior of light would revolutionize our understanding of electromagnetic radiation and open the door for the development of quantum mechanics. Planck's work also had important implications for the field of thermodynamics. His theory of quantized energy led to a deeper understanding of the behavior of matter and energy at the microscopic level. By introducing the idea that energy levels were discrete rather than continuous, Planck helped refine the statistical mechanics that governed the behavior of large groups of particles. This, in turn, provided a more accurate understanding of the relationship between temperature, heat, and entropy in thermodynamic systems. Moreover, Planck's quantum hypothesis had far-reaching consequences in other areas of science and technology. The concept of energy quanta paved the way for the development of technologies such as lasers, semiconductors, and quantum computers. These advancements have had a profound impact on modern society, influencing fields as diverse as telecommunications, medicine, and computing. Today, the principles of quantum mechanics continue to drive innovations in science and technology, further underscoring the lasting legacy of Planck's discovery. As Planck's ideas began to spread and gain acceptance, they triggered a revolution in the way scientists thought about the universe. The development of quantum mechanics, with its strange and counterintuitive principles, challenged the deterministic worldview of classical physics and introduced a new, probabilistic understanding of the physical world. Quantum mechanics has since become the dominant framework for understanding the behavior of particles on the atomic and subatomic levels, and it continues to shape our understanding of the universe. Max Planck's contribution to science cannot be overstated. His work not only solved the problem of black-body radiation, but also provided the intellectual foundation for the development of quantum mechanics, a theory that would go on to transform our understanding of the physical world. Planck's discovery of quantized energy was a turning point in the history of science, and it marked the beginning of a new era in physics. His legacy is a testament to the power of intellectual curiosity and the importance of challenging established ideas in the pursuit of knowledge. The impact of Planck's discovery extended far beyond his own time. It laid the groundwork for the groundbreaking work of other scientists, including Albert Einstein, Niels Bohr, and Werner Heisenberg, who would go on to develop the principles of quantum mechanics and revolutionize our understanding of the microscopic world. Planck's work is also a reminder of the importance of scientific inquiry in the face of uncertainty. The intellectual climate of the late 19th century, with its unsolved problems and unresolved questions, was one of intellectual ferment, and it was in this climate that Max Planck's breakthrough occurred. His discovery serves as a model for the scientific process, showing how moments of uncertainty and challenge can lead to some of the most profound insights into the nature of reality. Max Planck's hypothesis regarding the quantization of energy led to a fundamental shift in our understanding of the physical world. However, it was not without its complexities and challenges. As we turn our attention to the impact of his discovery and its subsequent evolution, we realize how his ideas paved the way for the development of quantum theory and, ultimately, quantum mechanics. Planck's insights laid the foundation for an intellectual revolution that transformed physics in the 20th century. After Planck introduced his revolutionary theory of energy quanta, it was Albert Einstein who took this concept further and applied it to the photoelectric effect in 1905. Einstein's work on the photoelectric effect demonstrated that light behaves not only as a continuous wave, but also as discrete packets of energy, which he termed photons. This idea, building on Planck's quantization of energy, was instrumental in explaining phenomena that classical wave theory could not, such as the ejection of electrons from metal surfaces when illuminated by light. In essence, Planck's work became the gateway through which Einstein's groundbreaking insights on the nature of light and energy could emerge. Although Planck's quantization of energy was crucial to understanding radiation at atomic and subatomic levels, he still viewed his discovery as a mathematical tool rather than a revolutionary principle of nature. It wasn't until later that the implications of Planck's work became fully clear. In fact, Planck himself did not immediately embrace the full scope of his own discovery. He thought of the quanta as mere mathematical devices to solve the specific problem of blackbody radiation, not as a universal property of energy. This perspective was consistent with his belief in classical physics, where energy was still considered continuous. However, as other scientists expanded upon Planck's hypothesis, they began to recognize the true depth of its significance. As Einstein's work on the photoelectric effect showed, the quantum nature of energy had far-reaching consequences for our understanding of light and matter. The photoelectric effect could only be explained by assuming that light consists of discrete quanta, or photons, which could impart energy to electrons. This idea upended the classical notion of light as a continuous wave and introduced the concept of wave-particle duality, the idea that light and other forms of electromagnetic radiation exhibit both wave-like and particle-like properties. Einstein's work won him the Nobel Prize in Physics in 1921, solidifying Planck's hypothesis as a critical stepping stone in the development of quantum theory. Simultaneously, Niels Bohr's work on atomic structure built upon Planck's ideas by introducing the concept of quantized energy levels within atoms. Bohr proposed that electrons in an atom occupy discrete energy levels and can only transition between these levels by absorbing or emitting specific amounts of energy. This was an application of Planck's quantum theory to the behavior of atoms. Bohr's model of the hydrogen atom successfully explained the spectral lines of hydrogen, which had previously baffled scientists. By adopting the idea that energy was quantized, Bohr's model marked a pivotal moment in the development of quantum mechanics and showed the practical application of Planck's ideas. While Planck's initial work on energy quanta solved a major problem in theoretical physics, it was the cumulative efforts of several scientists, including Einstein and Bohr, that transformed the quantization of energy into the cornerstone of modern physics. The 1,920 seconds and 1,930 seconds saw the rise of quantum mechanics as a fully fledged theory that could describe the behavior of matter at atomic and subatomic scales. Scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac further expanded on the quantum model, leading to the formulation of wave mechanics, the uncertainty principle, and quantum field theory. One of the most striking aspects of quantum mechanics was its departure from the deterministic worldview of classical physics. Classical physics, as described by Newton and others, held that the universe operated in a predictable cause and effect manner. If we knew the position and velocity of an object, we could predict its future behavior. In contrast, quantum mechanics introduced a probabilistic view of the universe. The behavior of particles, such as electrons, could no longer be precisely predicted, but only described in terms of probabilities. This uncertainty principle, introduced by Heisenberg, challenged the classical notions of certainty and determinism. The development of quantum mechanics also introduced the concept of superposition, the idea that particles can exist in multiple states simultaneously until they are measured or observed. This principle, first described in Schrödinger's wave equation, led to the famous thought experiment known as Schrödinger's cat, which illustrated the strange and counterintuitive nature of quantum mechanics. In this thought experiment, a cat inside a box is simultaneously alive and dead until the box is opened and the cat's state is observed. The implications of superposition and the observer effect were deeply unsettling for many physicists and philosophers alike, as they seemed to challenge our understanding of reality itself. As quantum mechanics evolved, it became increasingly clear that Planck's discovery had far-reaching consequences for our understanding of the physical world. The quantization of energy became a fundamental principle not only in the study of radiation but also in understanding the behavior of particles in fields such as chemistry, materials science, and even cosmology. The principles of quantum mechanics led to the development of technologies that have had a profound impact on modern life. Lasers, transistors, and semiconductor devices all rely on quantum principles, and they form the backbone of the modern electronics industry. Additionally, the study of quantum mechanics has provided the theoretical framework for emerging technologies such as quantum computing, which promises to revolutionize the field of computation. Quantum mechanics has also provided profound insights into the nature of the universe at its most fundamental level. The study of subatomic particles has revealed that the universe is made up of discrete packets of energy, and this has led to new theories about the fundamental forces that govern the cosmos. Quantum mechanics has contributed to the development of the Standard Model of particle physics, which describes the behavior of the fundamental particles and forces that make up the universe. It has also influenced cosmology, providing explanations for the behavior of matter and energy in black holes and the early universe, as well as the strange properties of dark matter and dark energy. The implications of Planck's work continue to resonate in modern physics and beyond. While the theory of relativity revolutionized our understanding of space and time, quantum mechanics transformed our understanding of matter, energy, and the fundamental forces of nature. Together, these two theories provide a comprehensive framework for understanding the universe at both the macroscopic and microscopic levels. However, despite their success in explaining a wide range of phenomena, there are still many unanswered questions at the intersection of quantum mechanics and general relativity. Physicists continue to search for a unified theory, sometimes referred to as a theory of everything, that would reconcile the two theories and provide a complete description of the fundamental forces of nature. In summary, Max Planck's discovery of quantized energy was the first step in a series of breakthroughs that would fundamentally alter our understanding of the physical world. His work provided the foundation for the development of quantum mechanics, a theory that has revolutionized physics and paved the way for technological advancements that have transformed society. Planck's insights into the nature of energy and radiation opened the door to new ways of thinking about the universe and its fundamental laws. The quantum revolution he helped initiate has not only reshaped the field of physics but also left an indelible mark on technology, philosophy, and our understanding of reality itself. Max Planck's legacy is one of profound intellectual courage, and his work continues to inspire scientists and thinkers around the world today. In the early 20th century, the field of physics was facing an intellectual crisis. While classical physics, with its elegant equations and time-tested principles, had been remarkably successful in explaining a vast range of natural phenomena, there were certain problems that these established theories could not address. The inability of classical physics to explain some critical aspects of radiation, specifically black-body radiation, pointed to a deeper issue. The scientific community had begun to suspect that the classical framework was incomplete, and the search for a new understanding was well underway. This period of uncertainty and unanswered questions set the stage for one of the most revolutionary discoveries in the history of physics, Max Planck's theory of quantized energy. Blackbody radiation had emerged as one of the most perplexing issues in physics by the end of the 19th century. A blackbody is an idealized object that absorbs all incident electromagnetic radiation, and it re-emits this radiation according to its temperature. Scientists had long known that the intensity of radiation emitted by a black body followed a predictable pattern that depended on the object's temperature. However, classical physics failed to provide an accurate explanation for the observed spectrum of this radiation, particularly at higher frequencies, or in the ultraviolet range. Classical theories predicted that the intensity of radiation would increase without bound as the wavelength shortened, a prediction that led to the so-called ultraviolet catastrophe. This contradiction between theory and experiment revealed that something fundamental was missing in the understanding of energy and radiation. At the time, classical physics, particularly the laws of thermodynamics and Maxwell's equations governing electromagnetism, were thought to provide a comprehensive description of the physical world. The classical view held that energy was continuous, capable of being divided into infinitely small amounts. This view had worked for the majority of observable phenomena, but when applied to the behavior of radiation emitted by a heated body, this assumption led to erroneous results. The intensity of radiation at short wavelengths, as predicted by classical theory, would increase to infinite levels, something which had no experimental basis. It was this glaring inconsistency that challenged the very foundation of classical physics. Max Planck, a German physicist, found himself deeply entrenched in the problem of black body radiation in the late 1800s. While working on his research in thermodynamics and statistical mechanics, he realized that the solution to the problem might lie in reconsidering the nature of energy itself. Planck proposed that the energy emitted by the oscillators inside a black body was not continuous but rather quantized, existing only in discrete, fixed amounts. This insight was not just an academic exercise. It had immediate and profound implications for the way physicists understood energy at its most fundamental level. Planck's proposal was radical and unprecedented. Energy could only be emitted or absorbed in discrete packets, which he called quanta. Planck's idea was deeply counterintuitive at the time. The notion that energy could not be divided into infinitely small parts seemed to defy all logic. After all, classical physics had been built on the premise of continuous energy, and this idea had been so successful that it was difficult to imagine a reality where energy behaved differently. Yet, Planck's proposal fit perfectly with the observed behavior of black-body radiation. By assuming that the energy of radiation was quantized, Planck could derive a mathematical expression that accurately described the radiation spectrum of a black body. This formula, which would later become known as Planck's law, was a breakthrough in theoretical physics. It provided a clear and mathematically elegant solution to the problem that had baffled physicists for decades. Planck's equation, E equals h, nu, where E is the energy of the quantum, h is Planck's constant, and nu is the frequency of the radiation, became the cornerstone of his quantum hypothesis. It showed that the energy of an oscillator inside a black body was directly proportional to the frequency of the radiation it emitted. This quantization of energy led to the resolution of the ultraviolet catastrophe and also marked the first real step toward the development of quantum mechanics. While Planck's formula provided a solution to the problem of black body radiation, it also opened up an entirely new way of thinking about the physical world. In introducing the idea of energy quanta, Planck had effectively set the stage for the scientific revolution that would follow. His work was groundbreaking, but it was only the beginning of a larger transformation in physics. Planck himself, however, was reluctant to accept the full implications of his discovery. He initially believed that the concept of quantized energy was merely a mathematical tool, a means to an end for solving a specific problem. He didn't fully appreciate that his hypothesis would eventually lay the foundation for an entirely new field of study that would revolutionize the way humanity understood the universe. It was Albert Einstein, in 1905, who expanded upon Planck's ideas and applied them to the phenomenon of the photoelectric effect. Einstein proposed that light, like radiation, was quantized and could be thought of as discrete particles, photons. This was a radical extension of Planck's hypothesis, as it suggested that light was not just a wave, as had been traditionally understood, but also exhibited particle-like properties. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it was one of the key moments in the development of quantum theory. The idea that energy could be both a wave and a particle was a fundamental departure from classical physics and paved the way for the later development of wave-particle duality. Planck's contributions, however, were not solely confined to his work on black-body radiation. His ideas had a profound influence on the development of statistical mechanics and thermodynamics. In the realm of thermodynamics, Planck's insights into quantized energy helped refine the statistical models used to describe the behavior of particles. By considering energy as discrete, Planck's work made it possible to more accurately model the distribution of energy in thermodynamic systems. This idea also provided a clearer understanding of entropy, a concept central to the second law of thermodynamics. As the years passed, Planck's quantum theory continued to gain acceptance, and it became clear that his work was a precursor to the development of quantum mechanics. Other scientists, such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, would take Planck's initial ideas and expand upon them, ultimately creating a fully realized quantum theory. This new theory would be radically different from the classical physics that had dominated for centuries. Unlike classical physics, which described the behavior of objects in a deterministic way, quantum mechanics introduced an element of uncertainty and probability into the laws of physics. This shift in perspective was a turning point in our understanding of the natural world and would lead to the development of technologies that have profoundly changed our lives. In summary, Max Planck's theory of quantized energy was one of the most significant breakthroughs in the history of science. His solution to the problem of black-body radiation provided a key insight into the nature of energy and set the stage for the development of quantum mechanics. Though Planck did not fully grasp the revolutionary nature of his discovery at the time, his work laid the foundation for the intellectual transformation that would reshape the world of physics. The legacy of Planck's ideas is still felt today, as quantum mechanics continues to be a vital part of modern science and technology. Planck's work marked the dawn of a new era in our understanding of the universe, and it remains one of the cornerstones of modern physics. Max Planck's discovery of energy quantization profoundly altered the trajectory of physics. His work on black-body radiation and the introduction of quantized energy levels marked the beginning of a paradigm shift from classical mechanics to quantum mechanics, a revolution in science that would transform not only our understanding of physics, but also the technologies that shape modern life. Although initially, Planck himself did not realize the full extent of his contribution, his quantum hypothesis laid the foundation for some of the most groundbreaking developments in science, such as the works of Einstein, Bohr, Heisenberg, and Schrödinger. The impact of his discovery, however, extended beyond physics, influencing other disciplines and technologies, and reshaping the course of human knowledge. The initial context of Max Planck's work is essential in understanding how his discovery came to be. The turn of the 20th century was a period of intellectual uncertainty in the scientific community. Classical physics, which had been the dominant framework for understanding the natural world for centuries, was encountering serious limitations when it came to explaining certain phenomena at the atomic and subatomic levels. One of the most perplexing challenges was the behavior of radiation emitted by a black body, a perfect absorber and emitter of radiation. Classical physics, particularly the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a black body at high frequencies would increase without bound, which led to the so-called ultraviolet catastrophe. This prediction, however, did not match experimental observations, which showed that radiation intensity at shorter wavelengths actually decreased after reaching a peak. The discrepancy between classical predictions and experimental results was a major source of frustration for physicists of the time. The problem of black-body radiation, seemingly esoteric, had become emblematic of the broader crisis in classical physics. While classical theories had successfully explained a wide range of physical phenomena, they were unable to provide a satisfactory explanation for what was happening at the microscopic level, particularly with regard to the behavior of light and heat. The limits of classical physics were becoming increasingly apparent, and it was clear that a new framework was needed, one that could account for the discrepancies in black-body radiation and similar phenomena. This is where Planck's work would make a dramatic and transformative impact. In 1900, while working on the problem of black-body radiation, Planck proposed a groundbreaking hypothesis. He suggested that energy is not emitted or absorbed continuously, as classical physics had assumed, but rather in discrete amounts, or quanta. This was a bold departure from the traditional view of energy as a continuous flow. Planck's hypothesis stated that energy is quantized, and that each quantum of energy is proportional to the frequency of the radiation. His formula, E equals h nu, where E is energy, is Planck's constant, and nu, is the frequency of the radiation, provided a simple yet elegant explanation for black-body radiation. By introducing this concept of quantized energy, Planck was able to resolve the ultraviolet catastrophe and explain the observed spectrum of radiation from black bodies. Planck's theory was initially seen as a mathematical convenience, an abstract solution to a specific problem, rather than a fundamental shift in the understanding of energy. Planck himself was hesitant to accept the full implications of his discovery, seeing the quantization of energy more as a mathematical tool than a new physical principle. He believed that energy might eventually return to being treated as a continuous entity once the temporary issue of black-body radiation was resolved. However, the scientific community began to realize that Planck's work held far more profound implications than just solving a single problem. The idea that energy could be quantized was a radical concept that undermined the classical view of the physical world. As scientists began to grasp the significance of Planck's discovery, it became clear that it was not just a solution to a particular problem, but rather the first step in a much larger revolution in physics. Although Planck's initial discovery solved the problem of black-body radiation, it was Albert Einstein's later work that extended Planck's ideas and fully developed the concept of energy quanta. In 1905, Einstein applied the concept of quantized energy to the photoelectric effect, demonstrating that light, which had long been understood as a continuous wave, could also behave like a particle. In the photoelectric effect, when light strikes a metal surface, it ejects electrons from the surface, but only if the light exceeds a certain frequency. Einstein's insight was that light consists of discrete packets of energy, or photons, and only photons with energy above a certain threshold frequency could knock electrons loose from the metal. Einstein's work in this area confirmed the validity of Planck's hypothesis of quantized energy and extended it to the nature of light itself. For this work, Einstein was awarded the Nobel Prize in Physics in 1921, further cementing the quantum hypothesis as a pivotal concept in modern physics. Einstein's extension of Planck's ideas was just the beginning. Niels Bohr, in 1913, applied quantum concepts to the structure of atoms. Bohr's model of the hydrogen atom suggested that electrons in an atom occupy discrete energy levels, and that they could only transition between these levels by absorbing or emitting specific amounts of energy quanta. Bohr's model successfully explained the spectral lines of hydrogen, which had previously eluded classical physics. His work on atomic structure, which was based on Planck's concept of quantized energy, became a major breakthrough in understanding the nature of the atom and laid the foundation for future developments in quantum mechanics. As the 1920 seconds and 1930 seconds unfolded, more scientists, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, built upon Planck's work and developed the formalism of quantum mechanics. Quantum mechanics, unlike classical physics, was probabilistic, not deterministic. It described the behavior of particles not in terms of fixed positions and velocities, but in terms of probabilities. This represented a radical departure from the classical worldview, which had been grounded in the idea of predictability. The principles of quantum mechanics, such as wave-particle duality and the uncertainty principle, fundamentally changed the way scientists understood the universe. In addition to its intellectual impact, Planck's work had far-reaching consequences for technology. The principles of quantum mechanics have been applied to the development of technologies that have transformed society. Quantum theory underpins the operation of transistors, lasers, and semiconductor devices technologies that are now integral to electronics, telecommunications, and computing. These technologies have revolutionized the way we live, work, and communicate, and they continue to be a driving force behind technological progress. In particular, the development of quantum computing holds the promise of a new generation of computing power, one that could vastly exceed the capabilities of classical computers. Moreover, Planck's work on the quantization of energy laid the groundwork for the development of quantum field theory, which describes the behavior of elementary particles and the fundamental forces of nature. Quantum field theory is the framework that underpins the standard model of particle physics, which has provided an extraordinary level of understanding about the nature of matter and the universe. Planck's constant, the fundamental constant in his equation, remains one of the most important constants in physics today, a symbol of the birth of quantum mechanics. In summary, Max Planck's theory of quantized energy was the beginning of a new era in physics. His work on blackbody radiation was the catalyst for the development of quantum mechanics, a theory that has since revolutionized our understanding of the universe at its most fundamental level. Planck's discovery shattered the classical view of energy as continuous and introduced the concept of discrete quanta, which would become the cornerstone of the quantum revolution. The legacy of Planck's work extends far beyond physics, influencing technology, cosmology, and our understanding of the nature of reality itself. Through his insights, Planck helped unlock the mysteries of the atomic world, and his contributions continue to shape scientific research and technological innovation today. Max Planck's quantum hypothesis remains one of the most important turning points in the history of science, and his legacy will continue to inspire and inform the scientific community for generations to come. Max Planck's groundbreaking work in the early 20th century revolutionized our understanding of the physical world. He solved one of the most perplexing problems of his time, the issue of black body radiation, by proposing that energy is not emitted continuously, as classical physics had long assumed, but rather in discrete packets or quanta. This insight was a radical departure from the classical ideas of continuous energy and laid the groundwork for the development of quantum mechanics, one of the most influential theories in modern physics. Planck's work shifted the way scientists viewed energy and radiation, challenging the established norms and offering a new path forward. Before Planck's hypothesis, classical physics, particularly the Rayleigh-Jeans law, had failed to explain the radiation emitted by a black body at high frequencies. Classical predictions suggested that radiation intensity would increase without bound as the wavelength shortened, a scenario known as the ultraviolet catastrophe. However, experimental observations did not align with these predictions. Instead of the infinite increase in radiation, the intensity of radiation at shorter wavelengths decreased, contradicting the predictions of classical physics. This failure created a crisis in the scientific community and highlighted the need for a new approach to understanding radiation. Planck's solution was revolutionary. In 1900, while trying to explain black-body radiation, Planck proposed that energy could only be emitted or absorbed in discrete amounts, which he called quanta. These quanta were proportional to the frequency of the radiation, and the energy of each quantum was given by the formula E equals h, nu, where E is energy, h is Planck's constant, and nu is the frequency of the radiation. This was a radical idea because it contradicted the classical view that energy was continuous. Planck's hypothesis not only explained the behavior of black-body radiation, but also introduced a new way of thinking about energy in the physical world. Although Planck initially viewed the quantization of energy as a mathematical tool to solve the black-body problem, the broader implications of his work soon became clear. Planck's idea of quantized energy would go on to play a pivotal role in the development of quantum mechanics. The concept of energy quanta was extended by Albert Einstein in 1905 when he applied it to the photoelectric effect. Einstein's work showed that light, traditionally considered a wave, could also exhibit particle-like properties. This idea, called wave-particle duality, was central to the development of quantum theory. Einstein's extension of Planck's work earned him the Nobel Prize in Physics in 1921, further solidifying the quantum hypothesis. In the years that followed, other scientists, including Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, expanded on Planck's initial ideas. Bohr applied quantum concepts to atomic structure, showing that electrons in an atom occupied discrete energy levels. Heisenberg's uncertainty principle and Schrödinger's wave mechanics were developments that fully embraced Planck's idea of quantization, forming the foundation of modern quantum mechanics. The principles of quantum mechanics challenged the deterministic worldview of classical physics, introducing the idea that particles behave probabilistically rather than predictably. This new understanding of the universe was not only intellectually revolutionary but also had practical implications for technology, including the development of semiconductors, lasers, and quantum computers. Today, the impact of Planck's work is still felt in every corner of science and technology. The development of quantum mechanics, sparked by Planck's insight into energy quantization, has led to groundbreaking advances in fields ranging from particle physics to materials science. The discovery of energy quanta also paved the way for the invention of technologies such as lasers, which are essential to modern communications, and quantum computers, which hold the potential to revolutionize computing. Planck's constant remains a key figure in the equations of quantum mechanics, a constant that bridges the gap between the macroscopic world of classical physics and the microscopic world of quantum particles. Max Planck's work in the field of black-body radiation was the first step in a series of scientific revolutions that would forever change the way we understand the universe. His discovery of quantized energy transformed physics, moving it from a classical, continuous view of the world to a quantum, discrete view of reality. His legacy endures not only in the theoretical frameworks that guide modern physics but also in the technologies that have reshaped society. Without Planck's insight, much of the technological progress we take for granted today, from computers to telecommunications, would not have been possible. His contributions laid the foundation for the quantum age, making him one of the most influential scientists in history. Max Planck's discovery that energy is quantized was one of the most pivotal moments in the history of physics. Before his work, scientists believed energy could be divided into infinitely small amounts, consistent with classical physics' deterministic nature. However, when faced with the problem of black-body radiation, a phenomenon where the energy emitted by heated objects didn't align with predictions from classical theory, Planck realized the need for a fundamental change in how energy was understood. Classical physics, particularly the Rayleigh-Jeans law, predicted that radiation intensity would rise without bound as wavelengths shortened, leading to the so-called ultraviolet catastrophe. Yet, experimental observations did not support this prediction, showing that radiation intensity instead peaked at certain wavelengths before decreasing. Planck's solution was both radical and elegant. He proposed that energy could not be emitted or absorbed continuously, but instead came in fixed, discrete units, or quanta. This idea was revolutionary because it fundamentally contradicted classical physics, which had long assumed that energy was continuous and could be divided without limit. Planck's formula, E equals h, nu, where E is energy, h is Planck's constant, and nu is the frequency of the radiation, marked the birth of the quantum theory. Initially, Planck thought of the quanta as a mathematical convenience to solve the blackbody radiation problem, not as a reflection of the deeper structure of nature. Nevertheless, the success of his theory in explaining blackbody radiation showed that energy levels in certain systems are not continuous but rather quantized. This insight would pave the way for the development of a completely new field in physics. Although Planck did not initially grasp the full significance of his own discovery, it was a breakthrough that would lead to a series of transformative developments in physics. The concept of energy quanta challenged the classical view of a smooth, continuous universe. It set the stage for a new framework, quantum mechanics, that would be built upon by others. Albert Einstein, for example, expanded on Planck's ideas in 1905, using the concept of quanta to explain the photoelectric effect. Einstein proposed that light itself could also be quantized into discrete particles, which he called photons. This idea was a critical step in the development of quantum theory, and Einstein's work in this area won him the Nobel Prize in 1921. Einstein's extension of Planck's work was foundational in understanding the particle nature of light and further cemented the quantum hypothesis as a key part of modern physics. Alongside Einstein, other scientists, such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, further developed Planck's concepts, leading to the creation of quantum mechanics. Niels Bohr, for instance, used Planck's quantum theory to explain the discrete energy levels in atoms, particularly in his model of the hydrogen atom. This model helped explain why atoms emitted light in specific wavelengths. The development of quantum mechanics introduced ideas that would forever change our understanding of the universe, including the uncertainty principle, wave-particle duality, and the concept of superposition. Unlike classical physics, quantum mechanics introduced the notion that the behavior of particles could only be described probabilistically, not deterministically. This shift in thinking represented a profound departure from classical physics. The impact of Planck's work went far beyond theoretical physics. It directly influenced the development of numerous technologies that shaped the modern world. For instance, Planck's work was foundational to the development of quantum electronics, including the invention of the laser, which relies on the principles of quantum mechanics to produce coherent light. Transistors, the building blocks of modern electronics, also have their roots in quantum theory. These devices have transformed computing, telecommunications, and numerous other industries, driving technological progress on a scale that would have been unimaginable before the advent of quantum mechanics. Max Planck's contribution is still felt today in both fundamental science and applied technology. His work led to the development of quantum field theory, which underpins the standard model of particle physics, describing the fundamental forces and particles that make up the universe. The principles of quantum mechanics are not just abstract theories but are crucial to understanding and manipulating the world at the smallest scales. The development of technologies like quantum computers which promised to revolutionize computing by solving problems that classical computers cannot, is a direct continuation of the quantum revolution that Planck initiated. Additionally, understanding quantum mechanics is essential for breakthroughs in fields ranging from materials science to cosmology, where researchers continue to explore the fundamental nature of matter and energy. In summary, Max Planck's introduction of quantized energy marked the beginning of the quantum age. His work challenged the classical understanding of energy, laying the foundation for the development of quantum mechanics. Planck's discovery not only solved a critical issue in physics, but also paved the way for some of the most profound advancements in science and technology. His legacy continues to influence modern physics, shaping our understanding of the universe and driving innovations that impact every aspect of modern life. Max Planck's discovery of quantized energy in 1900 marked a revolutionary moment in the history of physics. Before his work, classical physics, particularly the laws of thermodynamics and Maxwell's equations, had been incredibly successful in explaining a wide range of phenomena. The universe seemed to obey clear, deterministic rules that governed both large objects and the behavior of light and heat. However, as physicists delved deeper into the microscopic realm, the behavior of radiation posed a significant problem that classical theories could not explain. One of the most pressing issues was black body radiation, the radiation emitted by an idealized object that absorbs and emits all forms of electromagnetic radiation. The problem with blackbody radiation had to do with the intensity of radiation emitted by objects at different temperatures, particularly at high frequencies or short wavelengths. Classical physics, through the Rayleigh-Jeans law, predicted that the intensity of radiation would increase without bound as the wavelength of radiation became shorter. This prediction was known as the ultraviolet catastrophe because it suggested that objects at high temperatures would emit infinite energy, which was not observed in nature. The failure of classical physics to explain this discrepancy became a crisis for the scientific community, as it indicated that a new understanding of energy and matter was needed. In the face of this crisis, Max Planck, working in the late 19th and early 20th centuries, proposed an entirely new idea: energy is quantized. Instead of being emitted or absorbed in continuous amounts, energy is released in fixed, discrete units, or quanta. This concept was radical because it contradicted the classical understanding of energy as a continuous and infinitely divisible entity. Planck introduced a mathematical constant, now known as Planck's constant, and formulated a relationship between energy and frequency for radiation, E equals h nu, where E is the energy of a quantum, h is Planck's constant, and nu is the frequency of the radiation. His proposal solved the black-body radiation problem and provided a new way of thinking about energy at the atomic level. Although Planck's work initially aimed to solve a specific problem related to radiation, it had far-reaching implications that would completely reshape the field of physics. Planck himself was initially reluctant to fully embrace the idea that energy was fundamentally quantized, viewing his hypothesis as a mathematical tool rather than a breakthrough in understanding the nature of the universe. Nonetheless, his work laid the groundwork for the development of quantum mechanics, a field that would completely alter our understanding of the microscopic world. The concept of energy quanta opened the door to ideas that would challenge classical physics at its very core, leading to new ways of thinking about particles, waves, and forces. Albert Einstein, building on Planck's work, expanded the idea of quantized energy to the phenomenon of light. In 1905, Einstein explained the photoelectric effect by proposing that light behaves not only as a wave, but also as discrete particles of energy, which he called photons. The photoelectric effect demonstrated that light of a certain frequency could knock electrons off a metal surface, but only if the frequency of light was above a threshold value. Einstein's extension of Planck's ideas to light was critical in establishing the dual nature of light as both a wave and a particle, a concept that became fundamental to quantum theory. The development of quantum mechanics was accelerated by the work of other physicists, including Niels Bohr, who applied Planck's quantum hypothesis to the atomic model. Bohr proposed that electrons in atoms occupy discrete energy levels, and that they can only transition between these levels by absorbing or emitting quanta of energy. This model of the atom successfully explained the spectral lines of hydrogen, which classical physics could not. Bohr's work, along with that of Werner Heisenberg and Erwin Schrödinger, helped formalize quantum mechanics, a theory that radically departed from the deterministic view of classical physics. Instead of predicting exact positions and velocities of particles, quantum mechanics describes their behavior in terms of probabilities, fundamentally altering how we understand the microscopic world. Planck's discovery did not only change theoretical physics, but also paved the way for practical technological innovations. The principles of quantum mechanics are the foundation of modern technologies such as lasers, semiconductors, and transistors. These technologies have had a profound impact on modern life, especially in fields like telecommunications, computing, and medicine. The development of quantum computing, which holds the promise of solving problems beyond the reach of classical computers, is a direct result of Planck's initial insights into quantized energy. Without Planck's work, the rapid technological advancements of the 20th and 21st centuries, including the miniaturization of electronic devices and the advent of the information age, would not have been possible. The enduring legacy of Max Planck's discovery is evident in both fundamental science and applied technology. His work on black-body radiation and the introduction of quantized energy marked the dawn of the quantum age, a period that has transformed our understanding of the universe and led to the development of groundbreaking technologies. Today, the principles of quantum mechanics continue to shape the future of science, offering new ways to explore the universe's fundamental forces and particles. Planck's constant remains one of the cornerstones of modern physics, and his ideas continue to inspire generations of scientists and engineers seeking to unlock the mysteries of the universe at its most fundamental level. Planck's work, while initially seen as a solution to a specific problem, ultimately changed the course of physics and continues to impact every aspect of modern life. Max Planck's discovery of quantized energy in 1900 marked a pivotal moment in the history of physics. At the time, the laws of classical physics, which had been remarkably successful in explaining many phenomena, began to show their limitations. One of the most pressing issues was the behavior of radiation emitted by a black body. A black body is an idealized object that absorbs all radiation that hits it and re-emits it in a predictable manner based on its temperature. Classical physics, through the Rayleigh-Jeans law, predicted that the intensity of radiation would increase infinitely as the wavelength shortened, leading to what was called the ultraviolet catastrophe. However, experimental observations did not match this prediction, revealing a significant gap in understanding. This discrepancy led Planck to propose an entirely new idea, that energy is not emitted continuously but in discrete packets, which he called quanta. He suggested that energy could only be absorbed or emitted in specific amounts, with each quantum of energy proportional to the frequency of the radiation. Planck introduced a constant, now known as Planck's constant, which became a fundamental quantity in quantum mechanics. The formula E equals h nu, where E represents energy, h is Planck's constant, and nu is the frequency of the radiation, was the breakthrough that resolved the black-body radiation problem. Although Planck initially saw his hypothesis as a mathematical tool to solve a specific issue with radiation, its broader implications became clear only later. His work laid the foundation for what would become quantum mechanics, a theory that would eventually reshape our understanding of the physical world. Planck's discovery indicated that energy, which had been seen as a continuous and fluid quantity in classical physics, was instead made up of discrete units that could not be subdivided infinitely. This idea stood in stark contrast to the classical view of the universe, which assumed a smooth, deterministic framework where all things could be measured and predicted. Einstein was the first to build on Planck's work, applying the concept of quantized energy to explain the photoelectric effect in 1905. Einstein demonstrated that light, which had traditionally been understood as a wave, could also be thought of as a stream of particles, which he called photons. This concept, known as wave-particle duality, suggested that light could exhibit both wave-like and particle-like behavior. Einstein's work extended Planck's hypothesis and showed that energy could be quantized not just in radiation but in light itself. For this, Einstein received the Nobel Prize in Physics in 1921, reinforcing the significance of Planck's work and helping to establish quantum theory as a cornerstone of modern physics. As quantum theory developed throughout the early 20th century, it introduced a new way of thinking about the behavior of matter. Niels Bohr applied Planck's ideas to the structure of atoms, proposing that electrons in atoms occupied discrete energy levels and that they could only transition between these levels by absorbing or emitting specific quanta of energy. Bohr's model of the hydrogen atom successfully explained the spectral lines of hydrogen, which had previously confounded scientists. Bohr's work, along with that of other pioneers such as Werner Heisenberg and Erwin Schrödinger, led to the formal development of quantum mechanics, which introduced the idea that particles could only be described probabilistically rather than deterministically. The influence of Planck's discovery extended beyond theoretical physics and had a profound impact on technology. Quantum mechanics, with its principles of quantized energy and wave-particle duality, formed the basis for the development of technologies that have transformed modern society. The invention of lasers, semiconductors, and transistors, all of which rely on the principles of quantum mechanics, has had a revolutionary impact on telecommunications, computing, and medical technologies. Quantum mechanics has not only shaped the way we understand the microscopic world, but has also enabled practical applications that are integral to daily life. Planck's constant, the cornerstone of his theory, continues to be one of the most important constants in physics. It represents the smallest unit of energy that can be observed in the quantum world, and its presence in the equations of quantum mechanics underscores the fundamental shift in our understanding of the universe. The work initiated by Planck opened the door for future developments in quantum field theory, which underpins the standard model of particle physics, explaining the behavior of subatomic particles and the fundamental forces of nature. Quantum mechanics remains a central framework for understanding not only the atomic world, but also the cosmological and fundamental aspects of the universe. Max Planck's legacy is vast and enduring. His work on quantized energy was the first step toward a revolution in physics that would lead to the development of quantum mechanics. What began as a solution to the specific problem of blackbody radiation grew into a theory that would fundamentally alter our understanding of matter, energy, and the universe itself. Today, Planck's ideas continue to shape our exploration of the microscopic world and drive the development of technologies that have reshaped our modern world. The quantum age, which began with Planck's insight, remains a defining era in the history of science, and his discovery continues to influence both theoretical physics and the technology that defines our everyday lives.